I'm going to go ahead and get started with this video. This is the determination of the Ka for weak acids. Okay, and this is actually a pretty cool lab. It's very simple, and the idea behind it is it's pretty smart actually. So I'm going to explain kind of how this works and why we're doing it the way we're doing it, and hopefully this will make sense to you. Okay, so you're going to want to read the background on this one. The background here basically shows the typical acid reaction in water. Okay, so you got this equation right here. Now, the Ka expression for this obviously is going to look like this. Okay, products over reactants. We know that. What we are trying to do in this lab is we are trying to figure out the Ka of the weak acid. Okay, so here's the strategy. The strategy is this: if we can make this, if we can make this A minus, the conjugate base, and the acid equal in concentration somehow in this lab. Okay, if we can make those two so that they are equal in concentration, they will cancel out in this expression. And what we're left with here is Ka equals H3O plus. Okay. Well, it's kind of hard to measure just the H3O plus concentration in the solution, but if you remember, the pH is the negative log of the H3O plus concentration. Now, we can measure pH. We have pH meters, right? So what we can do is take the negative log of both sides of this, and what we end up with, the negative log of the Ka is equal to the negative log of the H3O plus concentration. Okay, and we can rewrite this as pKa equals pH. Okay, and that p just means we're taking the negative log of it. Okay, and so that's kind of the idea. So at the point where the A minus and the HA are equal, if we can get it to that point and then measure the pH of the solution, that also tells us the pKa, which is the negative log of the Ka. And once we know that, we can just 10 that number, and that will give us our Ka value. Okay, so that's basically the idea of the lab. Now the problem is, how do we get the concentrations to be equal? Okay, and we'll get to that in just a minute. There's some other background information here that you might want to know. There's information on polyprotic acids, which we've already talked about. So then you'll get down here to the pre-lab questions, okay? And it says phosphoric acid is a triprotic acid, and it gives you the values of the Ka1, Ka2, and Ka3. It should look pretty familiar because that was on the quiz that we took yesterday. So number one, write the chemical equation for the first ionization reaction of phosphoric acid with water. Okay, I think you should be able to do this. Phosphoric acid is H3PO4. When it reacts with water, it's an acid. So obviously you're going to have your equilibrium, and then I'll let you finish that, okay? But basically you're going to just write the equation for the first ionization, so for the first hydrogen coming off of the H3PO4, okay? And then they want you to write the equilibrium constant expression for this reaction, okay? And so the equilibrium constant expression here for this first reaction, I'm kind of giving this away. But that's okay, because I want to talk about number 3. So we're going to have H2PO4 minus times H plus, or I guess H3O plus, the way that we have it written here, divided by the H3PO4. Okay. Now, number 3 is asking what would be the pH of the solution when the H3PO4 is equal to the H2PO4 minus. Okay, now notice, again, this is like what we were talking about up at the top here. If these are equal, then they cancel out because they're on top and bottom here. And so you're left with Ka equals H3O plus. Well, we know what the Ka is for this reaction, okay? So this is a little different than what we're going to do in the lab, because in the lab we're going to measure the pH, not the, we don't already know the Ka. We're actually trying to find the Ka. Alright, so, but on this one we know the Ka, so we know that 7.5 times 10 to the negative third is equal to the H3O plus concentration. Okay, and we want to know the pH of the solution, so we're going to take the negative log of that number, and that'll give us the pH. Okay, so very simple pre-lab this time. Hopefully that makes sense. Alright, once you're done with that, oh wait, sorry, pre-lab's not done. So phenolphthalein would not be an appropriate indicator to use to determine the Ka1 for phosphoric acid. Why not? Okay, so back up here, we got to talk about the answer to this one. If you take the negative log of that 7.5 times 10 to the negative third number, you're going to get a pH of 2.12 or something like that. Okay, and so obviously if that's where the pH is going to be when this thing is in solution, then obviously we don't want something that's around a pH of 7. Okay, we're going to need something that changes around 2. So probably the best choice here would be the orange 4, because the orange 4 is going to change closest to that pH that we need. Okay, the orange 4 would change around, goes from orange to peach right about 2.5 or 3. Okay, what would be the pH of number 5? What would be the pH of a solution prepared by combining equal quantities of NaH2PO4 and Na2HPO4? Explain with an equation. All right, so I'm assuming that they give you those Ka values up at the top here. Let's see. I'm not seeing those values. Make sure I didn't just miss it. Oh, sorry. It's the H2PO4 minus and the HPO4 2 minus. Sorry, because once this dissociates, I don't know what I was looking for there. But on number 5, once this dissociates, you've got the H2PO4 minus in solution. And again, the sodium's also there, but we don't care about the sodium because it doesn't react with water because it's an alkali metal. And HPO4 2 minus. Okay. So you need to actually write the reaction for that second Ka for the PO4, H3PO4. All right, this will be the second reaction there. So it's going to be, I'm writing this below 6, but this is for number 5. So we've got H2PO4 minus in equilibrium with H plus HPO4 2 minus. Okay. And so the corresponding Ka for this one is going to be Ka2, because this is after the first dissociation has happened with the H3PO4. This is the second dissociation that happens. All right, so this will be Ka2. So they're just asking, when you have equal quantities of the NaH2PO4 and the Na2HPO4, what would the pH be? Okay, and so then you're doing the exact same thing that we did on the one above. You write the Ka equation. Ka equals H plus times HPO4 2 minus divided by the H2PO4. But then these cancel out because they're equal quantities. I'm being a little lazy on this one. The Ka is equal to the H plus or the H3O plus, depending on how you have it written. So then again, we know the Ka2 because they give it to us. Up at the top here, at the beginning of the pre-lab. So then, since we know the Ka2, just take the negative log of that, and that's going to give you your pH, because that Ka is equal to the H plus concentration, so then you take the negative log of that, and that gives you pH. Alright? So then, sufficient strong acid is added to a solution containing Na2HPO4 to neutralize 1/2 of it. What will be the pH of this solution? Okay, so this is basically the exact same question as number 5. You might not recognize it. They have a reason for asking this because this is kind of our strategy on this lab. But Na2HPO4, if you neutralize one half of it, that means that you have changed one half of it into its base, conjugate base. All right. So again, if we've got HPO4 2 minus here, and well, let's see here. Actually, we have to take that back because we're adding strong acid to it. So that's actually going to end up changing into H2PO4 minus here. So we want to know what the pH of that solution is. Okay, now honestly, this will end up being the same answer because it's basically the same thing as the one above, where you've got equal quantities of each of those in the solution. But you're going about it backwards. Okay, so this would actually, because we've got this equation written backwards, this would be 1 over Ka2. Okay. But then the expression is going to be switched also, right? So you've got 1 over Ka2 is equal to H2PO4 minus this products over reactants over H plus times the HPO4 2 minus. Okay, but then these are equal in quantities, so these cancel out, so you end up with 1 over Ka2 is equal to 1 over H plus. Well, we might as well just rewrite that as Ka2 is equal to H plus, okay? So, again, even though the reaction is happening in the opposite direction, we're ending up with the same concentrations of everything, so the pH is going to end up being exactly the same as number 5. Hopefully that makes sense. Okay, so Prelab took a little bit longer than I thought it was going to. I thought there were only 3 questions there. So that's that. Now, just talking about our procedure here so that you know what you're doing. Basically what we're doing is you are measuring out a small quantity of an unknown weak acid, okay? And it's going to be in solid form. And then you're going to dissolve it into exactly 50 milliliters of water, okay? Then what you're going to do is you're going to take 25 milliliters of that solution, and you're going to transfer it into an Erlenmeyer flask, okay? Then you're going to neutralize that 25 milliliters. In other words, you're going to add sodium hydroxide to it until you've completely converted it to base, okay? So at that point, you started with the weak acid formulas HA, right? And what you did is you added sodium hydroxide to it until you made an equal amount of A minus. So now you've got 25 milliliters of the HA solution that was originally there, right? Because you had 50 mils of this to begin with. Okay? Now 25 milliliters of it is the acid, and you just changed 25 milliliters of it into the conjugate base by adding the sodium hydroxide solution. Okay? And so once you did that, and maybe I should make this clear here. So you've got your HA, you added sodium hydroxide to it, which the hydroxide is the only part that we care about. And because sodium hydroxide is a strong base, you're completely converting this HA into H2O plus A minus, right? So however much HA we had over here, now we have exactly that same amount of A minus, okay? So in this bottom, in the Erlenmeyer flask, okay, you have completely converted it into A minus. So now you have exactly 25 milliliters of the HA of your original acid, and you have 25 milliliters of its conjugate base, okay? So then you can dump them back together, and once you do that, if you've got your Ka expression for this, it's going to be, sorry, that's the reactant. we got the H plus times the A minus over HA. Okay, because the expression for the dissociation of HA in water is H plus A minus. Okay, so I'm just writing the Ka expression for that. But now that we have sort of engineered the situation so that the A minus and the HA are equal in concentrations, now we've got that same situation we were talking about in the pre-lab, where the Ka is equal to the H plus. Okay? So that's kind of what we're doing on the lab. That's the plan. So you're going to basically mix those two solutions together, and then you're going to measure the pH of them. Okay? So what you're going to know here, pKa is equal to pH. You're going to know the pH, okay? And we know that because we have equal concentrations of the acid and its conjugate base, that's equal to the pKa, right? Once we know the pKa, all you need to do is take 10 to the negative of that pKa, whatever it is, and that's going to give you the Ka value, okay, which is what we're ultimately trying to find here. So that basically explains the calculations here. This lab is not going to be too bad as far as Postlab calculations. We should be able to finish all of this in one day. So this is telling you to do 2 trials for each of your unknowns, okay, and I'll put a number on the beaker so that you'll know which unknown is which. You're going to record the pH of each of those, and you're going to get the average pH, and then you should be able to find the pKa. These two blanks should be identical, okay? Whatever the pH is, that is your pKa. So then, once you find your Ka, then you can figure out your unknown, okay? Let's see, do I need to talk about anything else here? Average pH readings, Postlab calculation number 1, average pH readings, we just talked about that. Calculate the average pKa value for the unknown weak acid. Enter those in the data table. Comment on the precision of the pKa determinations. Describe sources of experimental error. Okay, you guys can do that. So you're basically just talking about how precise were these measurements. You can talk about sig figs there as far as our measuring using the graduated cylinders and that sort of thing. And the sources of error. Number 3, it gives a table that gives the identities of the unknowns that we had in this experiment. Okay. What you need to do is calculate the pKa for each of those. All right. So, and that's not hard. All you do to find the pKa of these Ks, just take the negative log of them. Okay. So, for example, the first one, negative log of the 6.2 times 10 to the negative, I can barely even read that. I think it's negative third. Let me double check that number to make sure. Nope, it's negative 8th. Sorry, it should be easier to read on your paper than it is on here. So that's the negative 8th. So you take the negative log of that, and that's going to give you your pKa value that you put here. Okay. So what you're going to do then, you're going to find all those pKa's, and then you're going to compare the pKa's that you got with your unknowns to these pKa's and see if you can figure out the identity of the unknowns. You're going to put that in the table right here. Okay. There will be a little bit of a component to this lab where I actually look at your identities there and see if you got them correct. Okay, this lab usually works out pretty well, so you should be able to figure out the correct unknowns here. Okay, and then it says compare the experimental pKa value for each unknown and the literature values reported in question 3. Determine the probable identity of each unknown and enter the answers in the okay. So we just talked about that. Write a chemical equation for the ionization of each weak acid in the list of unknowns. That one's the one that's going to take you a little while, but honestly, there's 1, 2, 3, 4, 5 unknowns there. All right, and so it's not going to take you that long probably to figure all those out. Why was it not necessary to know the exact mass of each acid sample? So I guess we can talk about that a little bit. I mean, do I want to let you figure that out, or do I want to talk about it? I think you guys can figure that one out. So we're not going to talk about that one. You guys can do that. Why was it not necessary to know the exact concentration of sodium hydroxide? Okay, so again, these two right here, I want you to think about what it was that we did in the lab, okay? How it was that we figured out that we had exactly, you know, half acid and half base in each of these beakers, and see if you can answer questions number 6 and 7. And then number 8 asks, why was it necessary to measure the exact volume of distilled water, as well as the exact volume of the solution transferred? Okay, so I want you to think about those three, see if you can figure them out. If you have questions about that, I can help you in class, but I don't want to give you everything here. So see if you can figure those out. And that's pretty much it for this lab. So a fairly simple lab. I don't think it's going to take you too long, and we usually get pretty good results for this one. So all right, we will see you in class.